Now, what I want to do, actually, I know that we're supposed to do CDCL, and actually, the way I structured this is there's a little bit of problems with this, but actually, this is a very good way to start structuring it. The idea is we basically need to um, go through the stack and kind of decide, which. Well, first we need to decide which variables are in conflict, and then when we find the conflict variables, we have to kind of make a decision on where to make some kind of cut so that we can not only go back in the backtrack, but we can also add a clause that would have prevented that um, whole tree traversal from happening. But we haven't done a tree traversal officially because we've only done one branch of that tree, so it'll prevent a whole tree from executing. So of course it would be much faster than DPLL at the point where we do get the clauses in and we do get the stack popped here. In fact, it'll become quite powerful. So, but let's write some visualization code. So how do we want to write some visualization code? Well, this is a great formula to visualize. So I would actually say that, this is the kind of one that would be really fun um, to see the whole thing here. So we do have, again, there's nothing particularly fun to visualize unless we have a graph. And if we want to have a graph, well, we can do several things here. But my opinion is, well, first off, we have the 2sat somewhere, which I can't find it. So we can visualize 2sat first, just so we can make our visualization framework and make it elegant and make it really nice. So the proposal would basically be that actually it's going to be very much the same code here. So of course I've got this SCC reach library that I've written that has the tarjan SCC. So it's a pretty easy algorithm to write. So it's not a big deal. So, I mean, we can see here the enumeration of solutions. Now, we could then, of course, draw lots of pictures. That's possible. 2sat visual. So what we're going to want is maybe like some kind of output file. Just right off the bat, we know we're going to want that. And so once we have the SCCs, yes, we could make a solution and stuff, but what we want to do is we want to output a digraph. Now, I've done this before using Graphies. I have the Graphies library installed for Python, so I mean that's the straightforward thing to do. And so the way you do this is just to draw some text. I mean, so I'm going to copy and paste some code. I already have to do this, but actually I even have a function that just does splice this stuff together. So we can just do something like that. Oh, but so we want the graph, so we don't want it to be so compact here. First, let's just draw the graph. That sounds good. So do graphies dot output or file name. Okay, that's how I do it. So the source will be the source text, and I guess we can just say make graphies dot text of successors. Let's just call it 2sat dot I think is the usual file name for this. Oh, I add the dot. Okay, we're gonna make an SVG and a dot file, so we'll just do it like this. So at this point, I just want to return. I just want to see this work. So uh, we're gonna need an output directory. Now, the way I've done this is usually I put it in like a test program file or something, and there's probably ways of getting this. Well, there's lots of different ideas for this. You could set environment variables, etc., and so forth. So what I do here is like this, and I think I'll do something like that because this is test code here, and yeah, this is really kind of sketchy test code because we should neaten it up a little bit, but um, we can do that at some point. Oh, look at that. Oh, I am using relative directories here. Yeah. So get satlib should have outdir. We'll call it config.dir, I guess. Okay, I mean, that should be sufficient. And then, of course, wherever we do this, now we can actually say, okay. Now this is going to pop up in my browser, actually. Fix some imports, do graphies dot not defined. Yeah, that's true. I have it in a library called graph. And we go to graph and we see what's going on here. Successors and text. I guess we don't need that. Yeah, just the way I structured things here. Guess we need to pass it as well. Okay, so that worked, actually. And so, uh-oh. It's not going to work very nicely, though, is it? Because I think it's going to keep popping up. Okay, I mean... Oh, no, it's working. Okay, actually, that's nice. So I can actually share the result here. And the way I'm going to do that is by adding a source. Browser. No, let's not do that, because problem is Graphi's pipe pops up where it kind of wants to here. Yeah, they found it. Microsoft did. So that's the graph. So the cool thing about this is now we're actually visualizing the SAT equation, the implication graph rather. This is not. This is saying that, you know, if 3 is true, then 4 has to be true. And if 1 is false, then 4 has to be true likewise. And so you can look for like loops in here. And if you know, something and its negation imply each other in a loop, then of course um, it's not satisfiable. So we get the SAT here, and or we get the SCCs. And it gets interesting here because now we want to change our visualization and we want to draw the SCCs somehow. One thing, we could collapse the SCCs, but what if we don't want to do that? Well, it turns out there's ways of doing something called clustering with graph Vs, and clustering requires you to add this subgraph. Now we actually have this graph Vs.text here, and we can actually kind of fix it up a little bit by saying, okay, we will add text. And so we can actually use this this make graphies.text. So what we need now is something that's going to make the subgraphs. So actually we want the SCCs. Now it gets more complicated because these are in topological order. And the other thing we want to do is actually we may want to try to draw the topological order. It of course it'll be more vertical, but actually that will be better if you think about it. But that's a separate complication from just maybe it's a separate complication. Actually, it's a good question. So I'm looking at the structure for this. Of course, there's better ways of concatenating strings in Pythons, but we'll just call it SCC underscore wait a second. This is returning, yeah, so it's returning a list of lists. And they are in reverse topological order already. One thing we can do is just take the first one. And we could just have some representative like header node for that strongly connected component. And then we need to add another space and a brace. And then we have like some style. We can fill it with color or not fill it. I think we do not want to shade it. So what we could do is we could fill the nodes as well. I mean, that might look okay. So we could do some like styling here. We say like node style equals filled. Again, this I'm looking at the GraphV's website for clusters. And I'm just copying off of that. Not like I memorized this stuff or something like that. Yeah. Finally, we can label that cluster as well, which is cool. So we'll want to add like a label at some point. So we have to add the edges, I suppose, for the cluster, which won't be the successors of the graph anymore. So now we have to think about that, right? We do have to think about that. So the successors we want to add are going to be the ones that aren't in a cluster. It's really, that's funky, but actually I think it's going to be beautiful. I mean, I think you'll see the difference between what I have on the screen. Oh, did I close it? Oh no, I didn't. Okay, it's here. Yeah. So this is really yeah, you know, I mean, it is what it is. It's an implication graph, but this is not like anything to be happy about. But if we put this in, I think it would be like 5 times better than it is right now. So you have to put the edges. That's okay. Uh, Efficiently, we don't care about efficiency for this. Drawing code is not something you use very often. And we can actually put a color for the box surrounding it. So we'll make the color blue. So the label, actually it's not very useful, is it? I mean, the label is just that it's a strongly connected component, but how useful could that be? Do we need a semicolon? Yeah, we do. Even so, yeah, I don't see a reason to put a label here. But I do see a reason to put the components here. So what are the components? Edges? Well, we can actually just filter those out from. Ooh, yeah. I mean, this is a little bit tricky because if we want to do this efficiently, we can take the successors and just filter them. That actually works quite well. And we can even just use what we already have here. If the successor stuff, ooh, yeah, dude, yeah. Oh yeah, that'll work just fine. So we can just you know, take the successor dictionary, and you know, it's x:y for I guess x in successors for y in successors of x. If and only if and this won't be efficient. But we could always use a different SCC structure rather than a list. Actually, none of this is efficient. This is terrible too. This is terrible. Yeah, SCC is a list. We don't want to do an inquiry for a list. It's just not a good idea. So ideally, we should actually convert this to a list of sets. In fact, I'm kind of like just sitting here asking myself, why don't we? Why don't we just do that right on the fly? It'll actually, that seems expensive, but it's O of n. But this is n squared. So you've like traded off O of n squared to reduce it to O of n. So even though it looks like you're doing something extra, this line of code becomes so much more efficient that you're actually doing something better. So this is where, you know, you have to think about programming. This statement right here is not efficient. It's O of n. It looks like it's doing some tiny thing, O of 1, but it's not. It's doing an O of n operation. And if we do one O of n operation out here, then in this double loop, we don't do, you know, n squared. Effectively, what? N and n. So, I mean, this is an n squared algorithm. Is it just n squared, or is it worse? No, it's n squared because even though this is a double loop, it's still effectively you're going through n things with this double loop. So it's n squared. Worst case, average case, I'm sure it's much better than that, but you know, nonetheless. And the order doesn't matter in here. So a simple idea is then to just say, okay, SCCs equals, you know, set of x for x in or set of SCC for SCC in SCCs. So I mean, this is a huge optimization. We could just do it like this. We don't want to add another line of code. In fact, I would argue that we should do it here too. While we're being efficient, we might as well carry on here. Yeah, I mean, again, these are subtle things, and I don't know why I didn't fix it before. A lot of this code's pretty good right now, actually. The way we ban solutions and do a lot, we're doing a lot of things in a very nice way. I think DP even is pretty good now. As I pointed out, there's like so many options with the optimization of the different rules that it's tricky, but I mean, at least it works. And at least it works in not a fast time, but it's not horrible. You know what I mean? For being the exponential kind of algorithm it is, and for using tricks to enumerate solutions, I mean, it's it's better than you would think it could be. Um, again, if somebody just tries to implement DP and doesn't spend a lot of time thinking about it, it's not easy to even get the time down to this. So, I mean, again, if you think about it more, you could actually get it even down further. But the way that I'm enumerating solutions, which it's not designed for, is pretty clever. So there is something to be said for that. So, okay, so anyways, after all that is said and done, if ooh, okay. Now the other problem we're gonna get here is now we need to delete these edges at the same time. So at the same time we do this, we also don't want those in the successors anymore. These are like the deletion edges, and that actually is a little tricky. I mean, because if we do them here, I mean, yeah, it will be tricky. Hmm. But again, we can of course find a way around that. It's not like the end of the world, but okay. Yeah, we don't need new lines and stuff. We could put tabs and new lines and format this. Probably we should, actually. If I look at the dot files and I see that they're horrible looking, that's not a good sign. But so SCC sub 0, the first node in the component, it's the representative. And basically, this should do the trick. So this can be a list, actually. It's a long line of code, but a very long line of code. But here we go. Wow. Yeah, I don't know what's going to happen anymore. Oh, set is not subscriptable. Yeah, okay, so let's not do that. Since we changed it to a set, there goes my immediately. Uh-oh. Int is not iterable. Oh yeah, what am I doing here? So first we check X, and then we can check Y in here. Yeah. Oh. Oh, this expects a string, so we should join them already. Oh man, that is one long line of code now. Maybe we should break it up. So let's see the dot text. Oh, SCC underscore -7. I wonder if that's invalid syntax. I'm not exactly sure what the issue is here. Could be like some little semicolon thing. Okay, there is a website I can just copy and paste this GraphViz code into. Like GraphViz Online Interactive, or yeah, GraphViz Online. So you search for GraphViz Online. There's a website. Wow, it has the exact code that I was just looking at for the clusters too. So. Okay, having this all on one line is a bad idea. I should fix that. So I guess we can't have a -8 inside. Yeah, so that's what I was thinking too. I said it looked ugly that we see SCC underscore -8, and immediately that is the bug. I mean, okay, I particularly don't like this kind of thing. Wait, where do I want to put this /n here? We're gonna beautify the GraphViz here. All right. Again, actually, all of it should be beautified. Again, it's just it becomes so much more useful not to see something that terrible looking. I can see these extra semicolons. Really, these are things that should be fixed. Now, I don't know how it got an SCC with no nodes in it. Oh, I know how. If the length of the SCC is 1, it should also skip it. That is either it's a trivial or a self loop. Well, in TwoSet you can't have a self loop, so it would be trivial. Okay, so the problem we said here was this SCC numbering scheme. Okay, fine. We'll just number the SCCs. We'll just make it I. By enumerating SCCs. And again, we may have like holes, I's that aren't in here because the length of the SCC was 1, but we don't care. It'll still be unique numbers, and that should. Oh, wow. Okay. Wow. We have a lot of doubled arrows. Okay, we can see that this looks a lot better. I can see extra semicolons all over the place. Okay, I see. Yeah, no, these are right. These are there are 4 SCCs. It's working, but it's of course doubling the edges because, as I said, we have to filter those out as well. Now the problem is we have to be able to query if 2 are in the same SCC. Now to figure that out, well, first off, when we're going through the SCCs, we could just eliminate from successors one option. Um, I mean, we could do a filter on successors like we do here, but then we would have to be able to efficiently query if, x and y are in the same component. Here we know x and y are we don't, well, we only have to check if they're in the current component, but again, what if they're not in the current component? But we need a way to map from nodes to components, and we don't have that right now. And that is a real problem. So if we want to fix this, well, we're going to have to either add that. It might be the way to go. Again, none of this is efficient, but we don't really care that much. Right? This is not, it's just drawing code, so again, it's not something to spend too much time on. More the time you want to spend isn't on efficiency, but on the actual graph v's functionality aspects to it. That's the better use of time. So let's just do that. Let's just yeah. I mean, again, I don't know. I mean, okay. For SCC and SCCs, and then for X and SCC, then we'll put okay. Remember, I enumerate. So, ooh, but this enumeration is also kind of it. No, actually, it's not a problem because we don't need to actually go find the SCC. If we did, that would be a problem, but we don't. We just need to know some number, some unique value associated with it. So we could actually just make a map from X, the node, to I. So we can just say node to SCC. So there you go. I mean, that works. And then this, again, this is getting really long, but we can just do the similar idea in here. X colon another thing for X in successors. Now, the one issue is we may end up putting empty values here. We could also filter those after the fact, because the problem is we could filter them here, but then we'd double the complexity. And well, not really. We'd same complexity, but double the work, even if the complexity is the same. Now, just because it's the same complexity doesn't mean you're not doing more work at the same level of complexity. Then so how I'm going to approach this is just to do the same kind of thing for y, y for y in successors of x. If node to SCC sub x is not equal to node to SCC sub y. All right. Honestly, that looked like it worked. Okay, I mean, looks perfectly reasonable. But what we don't have is all this nice stuff that we wanted here. This is a semicolon. Again, this is not pleasing at all. This is like, it's like we did nothing. You know what I mean? We've got all these subgraphs, but for some reason, I'm not exactly sure why this is happening. I'm wondering if this is the ordered. I think it's the order. I think we need to put the subgraphs. Still, I don't see the nice blue outline. I don't get this. Yeah, it's terrible. What if we put this like after this? Whoa. I mean, I don't get this. Actually, I'm looking at it in a different browser window, but I don't get it. I mean, it is shading them, but I don't have the nice boxes around them. I don't get it. I don't get it. I get nothing of the sort. I do see that the subgraphs need to come first. That much I do see. But even if the subgraphs come first, I don't get the nice blue shading around them, or the blue rectangle around the nodes, which is kind of weird. Was it because I used the rank direction from top bottom? No. Yeah, I don't get it. I don't get no matter what I'm doing, I don't get the very simple graphes example. What did they call them? Clusters. Do we need to use cluster underscore something? Oh, whoa. Oh, that's crazy. So you have to use cluster. You can't call them SCC. Huh. Huh. Ah, yeah, yeah. Okay, oh man, that changed everything. Okay, that's awesome. Now that's what we wanted. Okay, are we in reverse topological order here? So this almost looks good if we maybe do some shading just to show the ones. But the problem is we need an order for this. And actually we know, yeah, actually this is reverse topological order. This is great. Because 2 to 5 came first. So we see 2 to 5 here, and we see 2 to 5 at the bottom. And since it's reverse topological order, these will get assigned first, and then it'll go to 4. So then it will start assigning from one of these two, and then it'll keep going up, and as long as anything's unassigned, it'll assign. So we could end up with 2, 5, 4, and -3, 7, -1, but we could also end up with -7, 3, 1. I mean, both of those are possible. Uh, yeah, and so actually we can ban a solution, And then we could do the next one, and we could kind of watch what happens as we ban the solutions. It's really cool. We'll get like a storyline here. The only thing is this make graphies dot text is not going to cut it here. We don't want to use it because we want the text to come first, not after. So we just use the do graphies dot digraph thing here. Okay, and then I think this what it took a list. Oh no, it does, yeah, it takes a list. So we need our list of strings. So this string will just come second, and this one will come first. So we just reverse the order. And then it should look kind of nice. Okay, that looks a lot better. So this highlights the strongly connected components. It highlights the topological order, or reverse topological order, but actually everything is right here. There's nothing really left to be done here, but we're not done yet, right? We're not done. Why aren't we done? Because actually, as we said, we wanted to kind of go through the solutions. So we want to color things a little bit better than what we're doing right now. Now, how can we do that? Well, one thing is that it doesn't necessarily, as far as I know, it doesn't necessarily mean that you could have a conflict between a two different ones, but you could accept part of another node and this kind of stuff. So I don't think we can do the shading so universally. It could create some issues. But instead of the shading, why don't we just change? Actually, but I admit though, the shading is the most powerful thing we have right here. So I like the blue coloring around it, but yeah, I do. I mean, it does look pretty good now. This does, again, when you're making a good visualization framework, this is what you want. You want stuff like this. I mean, you can show anybody this picture of the two-sat equation, and they're going to be able to much more quickly start to figure out, okay, this is what's going on. These are the strongly connected components, the loops. They don't contain any of true and false together. And if we go upwards in reverse topological order, some 8 of those are going to get assigned. But the question was which 8 get assigned? Well, we could actually just add that to our graph at some point. So we do this here. Now, if it's unsat, then this might be what we want. Oh yeah, that's right. This is how we do it. We call all two sat. So we'll need to call all two sat with this f function. It'll pop up 3 different, for 3 solutions, so we can see them one by one, and it'd be nice. So this is just for one solution. Okay, so I think the way to do this here, I don't remember how to color the label of a node. I guess, okay, well, we'll try that. So the instinct here is that we're kind of like building a list here, right? So we can actually like say, why don't we just do that after the fact. So if it's unsat, yeah, I mean, to make this visualization framework really beautiful, if it's unsat, we want to draw the nodes in red that were the conflict nodes. Actually, we don't need to draw all of them, but we could. We could either draw all of the conflicts, but then we'd have to change this loop a little to find them, or we could draw any conflict, because any conflict is an unsat, and drawing all of them might just be elegance, just to say, hey, any of these ones would have worked, but um, instead of just showing you a random one, we'll show all of them to say, well, there's a bunch of reasons it's unsat, but of course, you just needed one of those reasons. So, okay. Let's take this to the next level here. That's handling that. And so if there's a solution, we do want to return the solution, by the way, because we're going to use all 2sat here, and so we still need eventually to be able to enumerate. And the only way we're going to be enumerating is if we do return our solutions. So we're going to be dumping out graph-v's files at the same time. We probably want to give different labels to these, but again, for now, we're not going to worry too much about all the details. Mainly what we do want here is to, add to dot here. And we want a string that basically makes green some of this stuff. So what would it make green? Well, everything in solution, Oh, this should go here. Something like that, I guess. Again, we have this option of making this one a little better and not just doing this x and minus x. Yeah, I'm of course not making this particularly easy to read graph-v's again with new lines and tabs like I should. Really should do that. Okay, that looks good to me. Okay. I mean, it's almost like we could make the single node ones. Okay, what if we don't check length of SCC as 1? Whoa. So I have to look at the clusters that... it's not putting the just single node there, yeah, alone. Well, you know, this is kind of like one of these little details of graph views here. But one to be solved. Because actually I like the way this looks now. It's showing us the solution too. It's showing how the topological search worked. It chose actually -8 probably first, and then it chose 5 and 2, and then it chose 4, and then it chose maybe 6, and then -3, 7, and -1. What we don't know is the exact order of the topological search, and that information we have, it's the order the SCCs are in. So we may want to like... That would be nice to be able to visualize. It's like the last piece of info. We know obviously it chose this one before this one. So, and we know that the problem here is that changing the color to green instead of shading gray. So gray means SCC, green means accepted in the formula. It's like an overriding dominant type of coloring. And yeah, the red, of course, we don't put all of them. And as I point out, that's probably... it would probably be nicer to just say, okay, we should just go through and find all of the x minus x in the same SCC and just do all of them here. In fact, that's very easy to do right now because we have this node to SCC structure. Anyways, something to think about. But the other thing is we want to... okay, now where do I do this? Style equals filled. So if we do it on the node, it applies to, I guess, all the nodes in the cluster. And color equals blue, I guess when it's in a cluster, it has that kind of application too, but we should get what we want here. Yeah. Okay. So now that's not too bad. As I say, the only problem, either we're going to have green or red. We won't ever have green and red in the same one because obviously it's not going to have a solution if it doesn't have a solution. Now, the only issue is how do we know the topological ordering that it went in? So here we see -8, then 2, 5. Yeah, like I said. Again, when there's edges in the graph, it's not too hard to figure out, I guess, that I'm assuming that yeah, but the problem is like the 6 could be done at any time, so I'm not sure how it picked these off. Because again, it was traversing this way, and then it's the way it came backwards that determines this reverse topological order. So 2, 5, 4, -3, -1, 7. Okay, so it chooses this one, and then it chooses the 6. What's interesting is it's very hard to actually, like, you know, put this information. I mean, we could put like a label on the nodes with the information in it. That's definitely one idea. It's probably the simplest of ideas, is just to, do that. I don't know if we could put a label on the graph too with the equation. Okay, label equals, so that's not too hard to do. Yeah, it might look awkward using numbers here, but again, you do want to see the formula as well. And so we can just say title equals, how do we convert a formula to text? Well, what we can do is we can take the, for clause in clauses, and we can, well, I guess V is, big V is or, and, oh, I don't know how to make an upside down V for an and. I'm looking up the ASCII characters for and or. There's also like some other symbols to do and or. I don't know if there's like a basic way. I mean, obviously a V makes a good. So I'm looking for logical and logical or with some kind of ASCII characters to just see if there is anything. Oh, well, I mean, there's ampersand, ampersand, and pipe, pipe, of course, but um, I mean, like if we look at Wikipedia, logical and logical or have special characters. Yeah, XOR can be a plus with a circle around it too. That's another thing we could do. There must be like a Unicode symbol or something. I don't want like a latex symbol because we're using graph fees. There are ways of intermixing graph fees and latex, I think. Oh, but I don't want to go there even if that's possible. Circle plus. Unicode? Oh, there probably. Yeah, there they are. Unicode characters 2A00 to 2AFF. I still don't see it in here, but it has to be here. Yeah, I see an XOR plus with a circle. Where's the V? Ooh, I don't know. Ooh, I don't know if GraphViz is gonna like this. Okay, we can fake it for now and worry about this later. Sloping large and sloping large or. Where's the actual large and large or? Double logical or. I'm just looking at the table here, trying to find it. I don't know why I'm certainly not finding it. Union or and. There's lots of cool stuff in this Unicode chart. Maybe I'm on the wrong page. I don't see it here. You know it's somewhere. If they have all these fancier variants. It's so weird. Hmm. Ah, here it is. Oh, 2227. Unicode 2227. Oh, there's an HTML. Now, there is a way to use HTML in Graphies, I think. How do we do that? Okay, I think this will work. So we can use HTML labels if you say label equals less than instead of quotes. All right, that was a lot of work to figure that out. So you can use ampersand and. Isn't that nice? Okay. Of course, this is conjunctive normal form, so we should do it like this. I know I'm doing something wrong there. Okay, there it is. Let's actually just call that formula for now. So that's how we make a formula. Easy enough. It's in conjunctive normal form. Now, can we get a beautiful label for this here? Wait, that didn't work. Yeah, ampersand and ampersand or. And there's the Unicode point values. I mean, we could. This should have worked. Label loc. Oh, what am I doing? Title. Surprised it didn't complain about that. Label loc equals top, and here's the label. I think it should support HTML for labels as well. Aha, look at that. Okay, now the one thing is that and would come before or, so we have to put parentheses here. Obviously, that's not going to cut it. Yeah, so that's it. I mean, there is our formula as a label with, and you can even copy and paste these things. That's nice. Honestly, I like that it's an SVG. We can copy and paste stuff out of here. The only info we're still lacking is, first, we don't print the implications from this. If we want, the implications are all double. So I mean, what we could do if we really want is we can actually, well, the implications are. Is there an implication symbol? Just for the fun of it. In HTML. Material implication. Wow. Oh, there's even a name for it. Wow, right? RR. RR. Okay. Material implication. Yeah, there's like a double kind of right arrow. Um, but I think this is the right way of doing it. So it's this right arrow. I guess RR is for right arrow, so that's easy. So we can actually write all of these um, implications, and then we just do the same thing, but now we get double. We get double the amount of things. And it's joined by and. Yeah, it's going to be lots of ands. So at this point, this would have worked for SAT even, but now we're into 2SAT because you don't have these implications unless it's 2SAT. So yeah, we go for clause in clauses. And we're going to join something with an and, which also is going to have another and in it here. So you just have to kind of do all of this. And so at this point, we're going to want not for, yeah, we'll just do for x, y in clauses. And we can just say stir sub x. Wait a second. It's not x. And then we have this implies. So not x implies y, and not y implies x. You can't, x doesn't imply not y. There's no other relations we can imply here. The only implications are strictly the ones that I'm going to put right here. So we'll put a break in, and then we'll put the implications. Will that work? Even? Whoa. Yeah, I mean, the problem is there's, as I said, a lot of implications, but that's pretty awesome. That is, I mean, just seeing that we're writing out everything, saying -1 implies 4, and -4 implies 1, and 2 implies 5, and -5 implies 2. Basically, this big graph we're looking at here. Okay, that is the logic here. Now, the I guess the only way we can label the topological sort, and close some of these tabs. So the only way I see, okay, of course I don't like how long this is. We should probably put lots more break statements in there, but you know, we can think about fixing that. But anyways, it gives us the formula. It's giving us the implications written in logic. So this is it's pretty beautiful if you think about it. So we've gotten rid of the ors, and we've just changed everything to and logic. So starts in conjunctive normal form, moves on to this form. And then we have a graph. The graph is colored, showing us what the true equation is, one possible true equation. Again, because it depends on the topological sort. And the only thing we're not looking at is this topological sort. So what we can do to fill that in, Okay, the way we're going to do this is kind of cleverly. Um, what we're going to need is we need an index. So we can put the reverse topological sort in either order. Again, we have the I values here, and I think that's sufficient. So we have I here, and what we can do, one problem is going to be is these single value ones. We're still going to need to like label them, but we could like we can play with the label here. Actually, it's to me that's the perfect thing to do. Is I said before we don't need a label, but now I can just back off on that and say, well, no, we do. Label equals. Actually, it's a very clean way to do it. And quote. So what do we want the label to be? Well, the topological order, I. See what happens if we do that. All right. So actually, I mean, that's not a well-placed label. But okay, one. Okay, well, it's printing them in a numerator, so we probably should make this 2, and this is 1, 2. And then the problem is, since we don't have the componenting around these single nodes, I think we just fix that. I think we just fix that. Yeah, it'll make the graph a little bigger, but it'll just make it so much more readable. Okay, so yeah, here we do it. One long line of code here. So the problem is these ones where the length of the SCC is just 1, and that's easy actually. Okay, so now we have all of our components, and we have the topological sort order. It's actually it's pretty beautiful. If you look at this it's just so clear. Obviously, this was the first one from a reverse topological perspective. The second, the third, the fourth, the fifth picked. By this time, by the sixth, it's already got these conflicting values, so it just doesn't choose any. So now the question is, can we just go into enumeration mode here? Let's do that. And let's call it like all 2sat with 2sat visual. And yeah, we're gonna, okay, so there's gonna be a little problem because the should just take clauses, but we can fix that. We can bind this. There's a way to do this using func tools or something, but I don't even care about that. I just want to see this this beauty work right here. So all 2sat is going to take test formula 3 and 2sat visual. Okay, so we're doing the binding here. Whoa. Wow. It's like a long-standing bug. Well, that's not very comforting, actually. It means my virtual machine code wasn't being tested right either. Doesn't make sense. So it's fixed now. Now I don't see this at all. That's weird. Test from the 3. All right, whatever. I mean, obviously it still works. Um, I don't know what's going on right now. This is mysterious. It's calling all 2sat. There must be... What on earth? This doesn't make any sense. This has got to be the weirdest... What? Oh. Never mind. I mean, of course, it was bad that I was calling not F, but 2sat here. But the problem is we need to actually force the enumeration to occur. Yeah, that's right. It's a yield function, so let's actually make it do something instead of just return a generator that we never use. Oh wait, that was my 3 solutions. Oh gosh. Try it again. I want to see them. But this is weird. Oh, I see. It's crashing in the graph stuff. Okay. Okay, okay, okay. So this will find a different solution because it's changed the order of these two. I guess, actually, was I missing that? 1 negative 7, 3. No, I mean, something's up. I mean, I see that it added 1. 1 or 1 means 1 is true. That's it. Like, it's effectively a unit literal. I mean, of course, it's also saying not 1 implies 1. Which means that not 1 can never be part of the solution. One, because if not 1 implies 1, that's an SCC, and that breaks it because negative 1 and 1 are in an SCC. So this actually is the two sat style way. I mean, of course, we could just put 1 there, but this is fine. That actually is right. We've banned the first variable from being the same again. And of course, actually, there's going to be a ton of wrong solutions here because we aren't efficient enough to. You're going to have to keep getting unsat, but I don't see all the unsat graphs popping up. And in fact, it's worse because I see the same graph popping up twice, and that should not happen. Yeah, you see, there's two graphs popping up, and when one is true. Oh, actually, I think I know what's going on here. Probably the problem is we're using the same file name, so we should probably stop doing that. Okay. So what's wrong with this? Yeah, okay. Again, we can see it blocking solutions now. So we see the SCC. And now the problem is, as I said, we could do all of them, and personally, I like it better. So personally, I would say what you do here is you don't do this. You change that to a string that's going to, I'm just thinking, yeah, we should only go through the positive or negative, the true or false. We don't need to go through both, or we get double. Yeah, so we can just say, um, so if x is greater than 0 and node to SCC sub x, is equal to node to SCC sub minus x. Okay. And then we can actually just do this. So yeah, I have to be careful with these semicolons is what I was finding out. Just comment that now. That's the first found solution versus this one. Uh-oh. Hello, angered gecko. Welcome to chat. I don't know, I may have missed you already. Yeah, I'm focused deep on this task. All right. Yeah, it's this stuff isn't always easy. Kind of some technical issues to debug here. I'm gonna get a coffee. One more coffee never hurt. Anyways, this subgraph clustering is really cool with graphies. I mean, this is like, I don't know. I think it's kind of elegant. Again, we're gonna have too many unsat solutions, which really we don't necessarily want, unless it was the first solution. So probably we need another like, probably we need some kind of status to know if we're enumerating, then we, versus if we're doing the very first one, you know, that's like the critical criteria on here. Okay, so what else do we need in here? We need the outdoor. Again, using the same file name over and over is not that good. Wow. Now we've got so many windows open here. Unfortunately, the browser timing for opening these files is coming into play here. I think. I think they might all be the same. Or it depends literally the moment the browser. Whoa. See this? I don't like to see this. I have no idea what's going on right now. Beyond that, probably we should, you know, use some kind of a unique file name. So, what basically we have to take all 2sat and we should count the number of solutions. That way, if it's solution 0, we deal with the unsat. But if it's solution any of these, we don't even print the unsat. Actually, it could be nice just to test the code, but you know, it's not really that necessary. This is like some kind of cheap trick here. Hash? How do you get a hash value in Python? Because we presume they're all going to have different hash values. Object.hash. Oh, hash of object. Okay. All right. Unhashable type list. Oh man, I'm just grinding this one out here. Yeah. All right, so let's see what those file names look like. Yeah, 2sat minus, yeah, it's a 64-bit one too. Okay. So this should be the last solution. Oh, this is just ridiculous. Obviously, these four should be colored green, and they're not. These should be colored green, and they are. This shows the forced solutions. That's great. This probably is a wrong one, so we can take a look. 4528-137. Yeah, these are all the ones that should be red. Okay, first off, let's make them red. All right, try it again. I know the last one's going to be green. Oh, maybe, no, maybe not. Actually, it doesn't, yeah. Okay. Wow. Yeah, that's good, because these are the only two not in a component, so they're all red. Okay, those are conflicts. This one, oh, that's why they're, yeah, in green. Okay, okay. These are conflict ones. Yeah. Yeah, because these are they're components with only conflicts in them. This is a solution. Honestly, quite good, I have to say. I mean, it's not bad. You see the topological ordering, you, everything. These graphs are big, for sure, but they're very informative of what was being searched and what was going on at each phase here. Yeah, okay, so I could make more optimizations to this, but actually I'm kind of saying I'm satisfied right now. We've done like literally the whole job. We just need to do a little bit more formatting. But in terms of getting the formula, getting the implication, the conjunctive normal form formula, the implication formula, the view of the implication graph, the strongly connected components clustered in an elegant way with boxes around them and labels for the topological ordering, coloring for either the things that caused unsat, all of the things, not anything, but just show all of them. And then at the same time, if there's a solution, we show the solution. So I mean, this is about as good as you can make it. Of course, if I'm doing the all, as I said, you should only do unstat once. You shouldn't do every. But we would need like some kind of state information about that, because then what we'd see is just three graphs here with the three solutions, and the ones that needed to be blocked would be shown there. Okay, so actually, I can't say I'm unsatisfied. I'm actually reasonably satisfied. Like we could actually apply this now to SAT as well. Like we've got something now that is pretty good if you think about it. And so we could actually look at SAT and model it as, you know, again, the graph is going to be quite different because you can't do these simple implications with a SAT formula. You just can't. It'd be nice, but you just can't. Uh, yeah, that's all there is to say about it. Anyways, the code here is kind of messy, I have to admit. But again, I got it to work in a quite nice way. So I don't need these comments here, do I? The any strategy. I actually I leave it as a comment for now because, again, there's two ideas. One is to show all of the different things that could have been found, because I think that's just more general and it shows more deep understanding. But also, the fact is that out of all of those, any of them was needed. Probably we should just put that one in like red and the other ones in orange. That would actually work as well. That would work. I have to admit that would completely work here. You wanted to be really, really clever. Although again, I don't know if there's any real advantage to that. So, anyways, that was it. So we've got all the information that I can think of basically being visualized here. Just in terms of enumeration, we aren't doing it right because we should only show the good solutions, except the unsat when it comes off the bat. Because these are like not the original formula anymore. These are just faked formulas for purpose of enumeration. And so actually, just come to think of it, I mean, it's kind of a cheesy trick here, but we could technically detect this, I guess. I mean, that's how to do it, right? So, one solution, two solution, and wow, I like it. I like it. And this was from last time. It's obviously we aren't getting it anymore. So that actually worked. I mean, we could just compare it with the initial clause. That was the easiest thing, and just hide the unsat if it's not the original clause anymore, because it's just a problem with our enumerator having to go through ones that are unsat along the way. So okay, wow. So the problem is the implication graph in SAT is something we're constructing. It's not based on the clauses. And in fact, we want to probably break this code apart. I mean, that was nice that we could do this, but um, yeah. So HTML SAT formula, I guess. So we're going to start doing this because we know that this routine is incredibly useful, actually. Um, but it won't be useful for the components part. So the clustering, well, again, though, but there's going to be different. It's a different situation over with 3SAT or KSAT or generalized SAT. So we can, of course, adapt our descriptions as we go. So formula implications. We don't need 2SAT. This is 2SAT specific. All right. And the reason I mention this is because it's pretty neat if we could get this to I almost feel like this should just be 2SAT, and all of this code should just be like a function call. Like here in unsat and here in before sat, like that should be it. Really, we shouldn't have much of this stuff going on at all. Although, I mean, it does change things a little bit, but yeah, because when we're doing it with SAT, we're going to want to show the implication graph that we've built and just how we're dealing with that. Again, we don't save the implication graph. Again, it's what's on the stack. It's that really we just have an implication branch, but that branch, if we're using CDCL, is going to learn stuff, and it's going to be incredibly important. So that's partly why I did this here, is because now we want to do CDCL, and now that we have a 2SAT visualization technique, we can adapt this to make, again, I've seen lots of pictures, but I think these are relatively elegant. Unfortunately, GraphViz doesn't format things maybe as compactly as I would like, but I have to say this is pretty nice stuff. It again, it looks pretty good because I'm looking at research papers and they're using like other possible frameworks to really compact things, and that is the one disadvantage here. But also, displaying cuts is going to be a little bit different than displaying clusters. So cuts are something going across edges. And I don't exactly know how to do that with GraphViz, but again, we have to figure that out. This is like very important stuff. Um, so I think we can just close this now. I don't see that we need it much anymore. Yeah, I can see how we block solutions here. Okay, just thinking about stuff. All right, so let's go to CDCL. As I say, I'm actually kind of happy with this right now, so um, I would say going to CDCL is okay here. Which means I want to uncomment this code. Probably I want to recomment this code. All right. Where were we? We were at CDCL here. All right, so this is where we have to like start rethinking CDCL. So I am cheating because I'm looking at a paper. Or no, not a paper, it's a slides. Slides that someone wrote. Lawrence Simon. I think I have this in here, don't I? Yeah, I do. I almost put this under CDCL because it's most relevant here. So I'm looking at these slides, which give a nice example so that I can kind of just visualize the different cuts. They're mentioning this FUIP term, which I'm not really sure what it is, but I should probably figure that out. Now, I am going to have to make my dinner and eat. I'm making a salad and just having that soon. But then I'm going to take a break, but I'm going to come back. I'm going to be back doing more of this visualization and finishing the CDCL. As well, I might just do more visualization in other areas like breadth first search and lexicographic breadth first search. I need to do more visualization pretty quick because I have to make some reports. And the best way to make a report that people can easily understand is to use visualization. I mean, there's no doubt about it. So that's something that I'm well aware of and I'm going to do. And as I point out, it's kind of fun making nice visualizations, even if unfortunately GraphViz just isn't giving the best layouts. It's very flexible because we could just generate anything at that point and we have something nice that can be shown to anybody. All right, so when there's a conflict, and there's something about this is not as easy as I was saying it is. We can go through all the clauses. We can take the values that have to be true, which means we can delete the negations of those values. The reason I'm thinking about this is because the problem is we've made like an arbitrary choice basically. So when we add a conflict clause, that's why we say the conflict vars, because actually we could have possibly chosen the alternate one, but now this becomes more complicated because it's like, well, but no, we couldn't have, not if the way we went on the tree forced one to come first. But if they came at the same level, that's a different situation. But that's why this is kind of complicated. So again, I almost want to just visualize what's going on here. Unfortunately, I think the cases are going to be too big, but doesn't matter actually. The browser can display a huge picture and we can kind of decide. Again, a picture is worth 1,000 words. It's much better than debugging with a textual console like I've been doing. It's just, the picture is definitely pretty good. Now I do have an example problem here, and I should think about encoding it. So from that slide set, we could take their problem, just so we can, again, we might not be able to force the same pathway too easily where they, force X1 and because we're just kind of doing things randomly, but somewhere or another they give 8 clauses, and 8 clauses is much better than 100. Yeah, probably 100 is just it's asking for trouble. So test formula 5. So it's equal to 1, 4. Yeah, actually, instead of saying 1 or 4, we should say x sub 1 or x sub 4. But I'm not exactly sure the HTML to do that. That would be a nice optimization. So 1, -3, -8, 1, 8, 12, and this will be a sat, because there's going to be a clause with 4, or 4 sat. 1, 8, 12, 2, 11, -3, -7, 13, -3, -7, -13, 9, and 8, -7, -9. So that's the example. Just check that I got it right. I think so. Ooh. Actually, well, it shouldn't matter that I know there's holes in the labels here. It's kind of awkward, I have to say, because I don't even know how many variables there are. I see 1, 3, 1, 2, 3, 4. There's no 5 or 6. There is 7, 8, 9. There's no 10. So there's actually 10 variables here. Yeah. I don't like this. I don't like this one bit. Because again, it should be, I mean, if you're going to present this, it should be relabeled to be minimal. But you could also test that it just works, because as far as I know, it should work. We're using a dictionaries and stuff, so it won't matter what the labels are. It just won't look as good to have these holes at 5, 6, and 10. Okay. I'm just going to replace this. I mean, I guess it's... What is it doing here? Oh, it's moving on already to the... Okay, so it's just skipping this, but hopefully we can start seeing if the clause learning is going to work here. But unfortunately, taking a random element from the dictionary, we kind of want to force it to be not x1, x3. We want to force the same order so we can, logically look at this and make the right cuts. So we go to CDCL, and from here, I don't know, the length of clause being 1 here just seems like it would just be a unit clause, and again, I don't see why that would tell us anything. I'm just wondering why it's not giving any output anymore. Am I just not waiting long enough? Well, let's see, 490. Yeah. Oh. So it's getting stuck. Whoa. Ooh, there's a lot of solutions. Ooh, that is very interesting. So we're missing solutions in our SAT enumerator, which means well, DPL is running extremely slow. And actually, it's funny because this is actually a relatively small equation, but um, wow. Yeah, and there's 10 variables and 8 clauses. And so this is kind of one that's pretty broad. There's 2,832 solutions to it. Uh, I generally would trust PySat. I mean, we could even try this one as well. We could try the SAT naive here. Yes, something's wrong with this one. Oh, isn't that interesting? Wait a second. This is weird. This is weird. I mean, since we make a set, there shouldn't be duplicates here. So what is happening? What is PSAT contain? How is it getting so many solutions? In fact, I mean, if the naive one, this is weird. Something is up here. Oh, I see. Yeah. Okay, so this has to do with it's times 8, right? And that's what we expect. Again, this has to do with the really bad numbering that's gone on here. So I think we should just renumber it because it's confusing them. They think that 5, 6, and 10 should just be free at this point. I suppose they are if we want to look at it that way, and we could just fix ours to make them free variables. Um, yeah, I mean, one thing we could do is just do like a clause 5, 6, or 10, and that actually will reduce the number maybe slightly, but it basically makes them free. But um, we, Yeah. And we could add a few more clauses to make it totally free. Yeah, that's better. So, I mean, at least, again, that's just a numbering issue here. But we also see DPLL is going to just run extremely slow to find such a high number of solutions. So personally, I think just get rid of it. We don't need to test this one. It's not worth it. All right. Anyways, that explains why we were getting different number of solutions. If they're not numbered consecutively, it just assumes they're free variables. And then, of course, it just, 2 to the power of that times extra solutions. And that actually is easy to count, even. So it's not a sharp p-complete problem when you identify a totally free variable. That is trivially 2 to the power of 3 extra variables. So, okay, so we go to CDCL now. And now we're kind of ready to, do something. All right, we might want to just put like a test code in here to say, well, that's kind of I simply want to force it to the picture that I already have, and that's going to mean -1. What is it? -1, 4, -7. Is that right? Oh, did they change the example? They did change the example. So for this example, it should be -1, 3, -2, 7. So it's kind of a hacky little solution. We could just, yeah, it's kind of hacky, and then we can just break else. I don't know. I mean, yeah, look at that. -7, 13, -3. Is that what I wanted? Yeah. Uh, mhm. It is what I wanted. And so basically, what is it? -7, 13, -3. Mm-hmm. Those are my conflict variables. So yes, we already have seven negative 13. Negative 13 was implied? 7 negative 13. Yeah. So we want to make a resolvent now, and the problem is we have to do some kind of backwards search here. So starting from the current clause and kind of going backwards, and we want to make some kind of a resolvent here. So I've basically forced this to do what I want it to do here. And we want to like get a little further on this. Whoa. Yeah, okay. So what we have here is 1, negative 4. These are the opposites of what we actually should have. And then we should have negative 3, 8, yeah, negative 3, 8, etc., and so on. However, if we look at the final clause, this is almost worth visualizing. Yeah, there's two ways of visualizing this, and I think we have to basically visualize both ways. One is the yeah, looking at the view of, you know, the decisions made and what clauses came about. The other, but the better way is actually to just visualize um, the whole implication graph, but put lines to split up the stack ordering of these things. Now, this is going to be some tricky business. I don't know how to do it in Graphies, but this is the thing we want to do. We want to make a nice visualization framework, and doing it in the primitive way, like I'm seeing for this example, versus another example which has a more complicated method. I think I like that visualization better, because this one is kind of, you know, not showing the implications beyond showing them at the clause level. Um, but they're both kind of useful. So maybe we combine them both into one graph. That would be my thought on this. So anyways, we have the conflicting variables. So at this point, any of those variables could be chosen as the key conflict. And ultimately, though, we're going to somehow need to resolve all of those variables. So when we see this situation, um, let's see. So the idea is the resolvent will be enough when it hits a literal from a unique literal from the last level, and that's exactly what it says, and that makes sense. So it starts the resolution with the on clause 9. Now 9 should be in here. It's not, though. Something's wrong. All right, I just want to check whether we've got -1, or we should have 1, -3, oh, 2. Yeah, 1, -3, 2, and -7. Hmm. Something's wrong with this, because again, why do we have -7 over here then? That doesn't make it. Beta 1. It's because it should be finding 9 as a variable that is causing a problem. And 9 is in the 6th clause and the 7th clause. So -7, -3, and 13 is the 5th clause. So it's saying there's a conflict in the 5th clause, which is true. I mean, there's absolutely nothing wrong about that. I see. The problem is, I guess the reason we're seeing a difference is because it's choosing negative. It's choosing instead of 13, it's choosing -13, which changes things a bit. But it shouldn't change things that much because it's chosen what negative. We have 8 here. Yeah, that's fine. 8, which means -8. Seven. Yeah, it's true. If yeah, it's interesting. So it totally changes things depending on the order it finds things in. Hmm. Which is actually, it's something hard for me to do anything about, because now this is no longer the decision tree. This is occurring in the unit literals. It just happened to choose uh, -13 and not 13. And if it does that, actually, it's going to end up leading to a different cut. And so this is right. That's the bottom line. This is right, and this actually has to do with clause number 5. So what we need at this point is to figure out the clause at this level which has led to the contradiction and what value forced it. So now we're going to have to do some kind of search here. So basically, this actually isn't enough information here, because what we need is yeah, we can't do that. We definitely cannot do that. So we need the current conflict. Next step. So the current conflict, there we are, 7, -9, and 13. And so we know that, one of these unit clauses is causing this conflict. And we also know that, again, since it chose -13, not 13, we get a kind of different scenario of what's going to occur here. What we can do is we can figure out, basically, we know that these unit literals have caused conflicts in these variables. So it has to be, we've made it 7, but we've end up forcing 7, but we're also saying, hey, -7 was deleted everywhere, and it couldn't be deleted everywhere. So it also should have been basically true. Or 13, it should have been true, or -3 should have been true. So, but again, the -3 is different because that would have occurred at a different level. So we ended up kind of making a problem with this one, but again, it's not going to be our focus. Our focus is mostly going to be looking at the clauses which led to the conflict, having to do with these different clauses right here. And the thing that's a little complicated to me is like, well, since we've got 3 different values that occurred here, how do we know which one to start the resolution with? So, well, -9 seems like not one to start the resolution with, even though it's used in the example. In this case, since we've gone with -13, it does force -9. But 9 isn't forced, so actually there's no conflict there. So I would say we have to start with the ones in here whose negations are in here. So we start with 7 and 13 and -7, -13. We've got these 2 variables, and basically we can just start building a formula at that point and deciding 13 and 7. I know I have to. This actually, it's a bit tricky to do this correctly. Well, basically, we could look at the 2 clauses. There's going to be one that's got a 13 and a -13 in it, and there's going to be one with that 7 and -7. Now, again, the problem is we don't really have a good dependency ordering here. So one of these could have forced the other one, and actually we need to go in order. So this is starting to look more complicated than I wanted it to be. This is like, this is interesting. Because even at this level, we need to kind of define the clause forcing order. So, however we have it, right? We have it because we know that 7 came first. We know that 13 came after 7. It's not to say 13 couldn't have forced 7 too. Sometimes maybe you could have 2. But we know that in this case, the order that it's returned in is the same order we did the unit propagation, which is very useful. So we know 7 forced -9, which forced -13. So we'll want to resolve on 7 first. So, but what we do is we look at the clauses including 7 and -7, which have all other, or we look at the 7 -7 clauses, which were forced here. I just want to make sure that that's right. It's 13. Yeah. So it looks like we go in the same order. So we'll start with 7, and then we'll move on to the yeah. And then we'll move on to -9 and -13. And basically, we just want to make a resolvent for all of these different ones. Actually, I guess we have to start with the conflict variable first. Might help to draw the picture. Again, the complicated thing about this is, again, we can look at the 7, -7 case, and we can just join it into a new equation. Actually, that's basically what we're doing. But we have to determine which one caused this conflict first. This is trickier than I want it to be. FUIP. Okay. All right. Seems like multiple conflicts. It's kind of an issue. I mean, we force 7. But actually, yeah, 7 should be first. But we haven't gotten the -7 quite yet. It wasn't till I know I'm feeling there's some faulty assumptions going on here. Like, the problem is maybe I'm over propagating, because the minute the propagation finds a conflict, I think you need to stop. Because if I stop, then I can take the conflict, I can use the resolvent strategy that we use, like the case splitting strategy, right on that. And then I can propagate the rest of the things that led to that. And then we can try to figure out where to jump back to based on that. It should be basically as simple as that. Okay. So actually the 7 case looks like the one we don't need to. Again, that can't be, that wasn't forced. That was chosen. So the first element here is always going to be the one that was chosen from the last step. So actually it's not forced. So we want to do a resolvent on 13. Again, if we found 2 conflicts, we need to do 2 resolvents, and that's a big problem. The minute we find an empty case, we may want to just exit. In fact, I'm kind of wondering why we don't. Would it cause a problem to do that? We do this one already. So I personally am thinking this is the only real way forward, is the minute we find a conflict, we should actually resolve that conflict. I mean, if we find propagated conflicts, we're going to end up getting explosively large clauses to add, and we're going to have to figure that out too. We actually need to know that, this conflict uh, potentially is leading to the next conflict. But then again, I'm also thinking, does it matter? Well, I guess the problem is it'll just be hard for us to decide which one caused the conflict. Whereas if we return right now, we know that the last solved vars is the conflict. We know the first one is the forced value, the last one's the conflict, and anything in between was the chain. And that actually is incredibly useful because it makes it so easy to add a resolvent here. So basically, we know the conflict occurred at this level. We know that the last value of this occur conflicts of -1. We know that it was forced. And we know it was forced because, it was the last remaining one. So it will be the last remaining one in some clauses. So we actually have to go through all the clauses again. And we need to figure out why it was forced. So again, there is kind of this weird well, what if the unit literals told you which clauses were the reason for the force? So we don't just return the solved variables, but we return which clause led up to that. Now, there could be multiple, actually, but yeah, I mean, but if they're resolving one by one, then it shouldn't be there unless there's duplicate clauses. But presumably we don't do it. But presumably we want to remove the duplicate clauses. So, and we could, again, we could do that up front. So if we took the last one, for example, we could, now we want to look for something different. We want to look for, wait, solved vars is, yeah, so we could just, say something like this. Oh yeah, I guess no. It could force two different variables simultaneously. Well, but we want to find out the ones because we're gonna just make a resolvent on any clause that forced this one. We're gonna make a resolvent, and after we have that resolvent, we're gonna work backwards down the chain and continue making resolvents. But the problem is, while we're doing that, we want to know in those resolvents there's more forced variables previously on the stack or up the stack, and we want to know where, what level we're getting to as we're doing this, so we can jump back. So the higher the level we get to, the better, because we can save some work. And that's the whole point of this algorithm. Okay, I need to eat dinner, and I'm going to come back and finish this off as soon as that's done. Basically, I have the intuition now on how to do this. I would like to make the visualization, though. It would be really, really nice to see that. But that'll come next. So, okay, I come back after.